So let's talk about the first kind of carry propagate adder, the ripple carry adder. So this adder, we're going to, put our 1-bit adders here, and we could potentially use just a half adder on our 0th bit. We're going to add those 0th bits, A sub 0 and B sub 0, and produce our sum bit, our sum 0 sub 0 bit. There's our adder there, in this case a 1-bit half adder, and we have our carry out here. This is C sub 0, the carry out of column 0. So if we had our example from before, 1 0 1 1 0 1 1 1, we added those together. Here's A sub 0, here's B sub 0, and our sum S sub 0 would be 0, and our carry out of column 0 would be, in this case, 1. Okay, so we want to feed that into the, as we can see from our addition here, this is the carry in of column 1. Remember, column 0, column 1, column 2, and column 3. And so we feed that into column 1. Right, this is the carry in input of this now full adder, A sub 1 and B sub 1. So now we're going to add these, these next bits, A sub 1 and B sub 1. And add that to our carry in here. That came in from the carry out of column 0. And we'll produce our sum bit, S sub 1, for the first column, right, the 0th column, now the first column, and we'll produce a carry out, C sub 1, or, right, we're either a 1 or 0 on the carry out. In this case, 1 plus 1 plus 1 is 3, so we get 1. Our carry out of that column 1, is 1 in this case, and it's going to get carried in to the next column 2. Okay, so same, same pattern here. A sub 2 and B sub 2, we're going to add those. We're going to add that to the carry out from column 1, which is the carry in to column 2, column 0, column 1, column 2. We're going to produce sum bit 2 and the carry out of column 2. And so forth, right? We could make a 32-bit adder or a 64-bit adder or whatever bit adder in the same way, but we can see that the slow path is where this carry ripples through our adders until the n-1th bit. So that path is pretty slow, but pretty simple. We use full adders, or possibly a half adder on that rightmost or least significant bit. And so here we have it drawn with, in this case, is a 32-bit ripple carry adder. Ripple carry adder. And so we can ask ourselves, well, what is the delay of this? Well, we get this pretty quickly, right? A sub 0, B sub 0, and potentially a carry in. We'll see why we might want to keep that as a full adder and have that as a carry in. Allow it to have a carry in coming into it on that least significant bit in the 0th column. Well, that's not the slow path though, right? That's not the critical path. If we put our numbers in A and B and are waiting for the result, well, the slowest path is through, right, through the carry chain. And so if we're thinking about this for 32 bits, well, we have one full adder delay, right? The delay to take these inputs and produce that carry out output. And then that comes in, another full adder delay to produce the carry for the next column, C sub 1, and so forth. So the delay for this is, in this particular case, 32-bit adder, 32 full adder delays. We designed a full adder up, in the previous slides, and so we could figure out what that delay is from our gates, individual gate delays. And generally for an n-bit adder, it's n times the full adder delay, because that carry has to ripple through each of those full adders. And so this is pretty slow, and this is one of the disadvantages of the ripple carry adder, but it's pretty simple too. So if we're looking for something that's cheap and speed isn't an issue, not a bad option. One thing I also want to mention here is that we write, unlike other circuits, we're actually writing it with the flow going from right to left, right? We typically have our gates with our flow going left to right. In this case, the flow is going right to left, and we do that because we want to keep our digits with our, least, how we write it. So our least significant bit is here, our LSB is here, and our most significant bit is on the left, as we expect with our numbers, right? If we have some number like the example we have, we put our MSB on the left and our LSB, our least significant bit, on the right. And so we draw our adders flowing from right to left. So again, the delay of our ripple carry adder is, well, n times the full adder delay, where TFA is the delay of a 1-bit full adder.